Hello, my name is Noson Yanofsky. We're doing, this class is called The Outer Limits of Reasoning, and we've come to the end of our journey together. So let's just recap. The class was about limits of reasoning. We talked about philosophical problems, we talked about language problems, we talked about sets, we talked about computers. We had 2 chapters on computers, but I wanted to give you, the class is all about limitations of reasoning, so I wanted to give you a taste of some of the other things that you will find in the book and other limits that you can work through. So really this should be a central part of the class, but some people find the science part a little bit painful or too much to do. So what I just do is do a taste of it. So I do a taste of chapter 7, which has science, okay, section 7.1, and a taste of chapter 9, which is about math. Okay, so we're going to do these 2 little things today, and you get a feel of what the rest, and again, the goal is to whet your appetite to read the rest of the book and to see some interesting things, and I hope you'll do that. Okay, so let's talk about chapter 7. Chapter 7, section 7.1, is about something called chaos theory. And we're going to talk about this. So I like to start off with a little story, and the story is not mine. The story is told by somebody else, but it's worth thinking about this story. So the story is about a man who is walking down the street, and there's a guy fixing a roof, and his hand is slightly a little bit wet or sweaty or something, and a tile from the roof falls down, hits the man in the head, and kills him. Okay? Not a pleasant story, but it's a story. Okay, and the question is as follows: what's the moral of the story? Okay, what is the moral of the story? Okay. It's very hard to do this without a classroom. Usually people say, well, bad things happen to good people. But what happens if the man who was walking in the street was a very bad man, okay, and he was a mass killer? And this roofer who dropped this thing killed this very bad man, which saved thousands of people's lives. So it's not really true that, that's the whole thing. Some people say that random things happen, but actually nothing random happened. In fact, when a person works, he gets sweaty. Sometimes he gets sweaty, and that makes sense. And when you're sweaty, you sometimes let things slip out of your hands. That's typical. That's almost expected. The fact that it landed on somebody and not just landed on the floor, I don't know, is that random? I mean, he was walking right there. Well, anyways, there's a lot of moral things you can learn from this. Well, what's the moral? There's no moral, but just what do you learn from this story? And what I'd like to say is as follows. What you learn from this story is as follows: that little changes can make major differences. Okay? Small changes in life can make major differences. For example, had the man dropped the tile 2 seconds earlier, then the guy walking in the street would have been past it. Or had he dropped it 2 seconds later, he would have been before it. In other words, these slight things. Had his hand been slightly less damp, maybe he wouldn't have fell. Had it fallen, but he would have fallen over there and it would have been caught by the gutter or something like that. Little changes make major changes in the universe. Okay? And by the way, this man who was walking in the street had a child, and the child has to now grow up as an orphan. So his life changed in many ways. Again, just by a little bit of water molecules on a hand can make major changes in life. Okay? Now, we know this. Okay? Anybody who's ever driven a car realizes if they're driving on the highway at 60 miles an hour and they go like this, people's lives have changed in many different ways. Okay, here's some other little changes that could happen that make large changes. Okay, if you had only chosen 42 instead of 43 on that lottery ticket, okay, whatever the lottery ticket is. If that death row pardon had just occurred 2 minutes earlier, that's it's a song. If only that bungee cord, you know, bungee jumping, people jump off, if only that bungee cord had been a little bit stronger, okay, you can figure it out. Okay. Anyways, the amazing thing is that small differences small changes make major changes in life. We know this, okay? But scientists started getting into this in the 60s, and I'd like to tell you a little story of how. Okay, in the 1960s, there was a mathematician there was a guy who was studying weather patterns, okay, in the 1960s. His name was Edward Lorenz. Okay. And this is the early 1960s, and he was working with some ideas of how the weather works, okay? So he figured, you know, he was coming up with equations that they take into account how strong the sun is, how close you are to the sea, because then the wind comes off the sea, or how much humidity there is in the air, and how much rain there was, how much rain there will be, how much rain there was, whatever, how things are changing all. Now, all these things affect each other, okay? So, for example, if there's a lot of sunshine, then you're going to get a lot of clouds, because it's going to boil up the thing. If you're going to get a lot of clouds, you're going to get rain. If you're going to get rain, by the way, the clouds stop the sunshine, so they affect each other positively and negatively. If there's a lot of wind, then maybe the clouds will blow away. All types of meteorological types of things. But he was coming up with equations, and what he wanted to do was he wanted to run these equations on a computer, do some simulations on a computer, and get the computer to come up with predictions, and things would happen. Things were happening. Anyways, so he was coming up. Now, this is early 60s, so they didn't have great graphics in the computers, and they were just coming up with numbers. Okay, so he set up a scenario, and he watched the computer come up with different things going on. And the way it was doing it was printing out different numbers, and the numbers were telling it how much the wind was, how much sunshine there was, how much different things there were. Okay? Anyways, one time he was watching a simulation, and the weather pattern started getting very interesting. But it was late. Okay? It was late. And so he wanted to go home and go to sleep and then come back in the morning and redo it. So what he did was he printed out the numbers of what he was watching, okay? And what he did was he stopped the computer, went home, went to eat, went to sleep, came back the next morning, and rather than putting in the numbers, okay, and I actually looked this up, one of the numbers was 0.506127. Rather than putting in that whole entire number, the next morning he went and he typed into the computer, because he wanted to continue to see that interesting weather pattern. So rather than typing this, he typed in 0.506. And now, obviously, he had to put in more than just one number, but it was a couple of numbers, a few numbers, describing all the things. And he said, okay, now, let me see. Last night I was watching this weather pattern form. I'd like to watch it again form. Okay? So, but he was lazy, and rather than putting in this, he put in this. Now, notice that the difference between this and this is, you know, the tens, the hundreds, the thousands. The difference between this and this is 1/1000th of a difference. Well, 1/10,000th of a difference. No? What's up? Okay, it could be up to 1/1000th of a difference. Whatever. It doesn't matter. It's a little difference. But you know what he found? Well, doing this lazy way, instead of putting in all the things, he got totally different weather patterns. He got In other words, he was watching some weather patterns. He started a little bit earlier and put in these instead of these, and he got a totally different weather pattern. Now that's an amazing thing, because you would think, oh look, instead of putting in 506, 127, what's the difference between this and this? It's nothing. Okay, it's 1/10,000th of a difference. But he did that, and he saw he got totally different weather patterns, and he was absolutely fascinated about this. And he started writing papers about this, and one of the papers that he wrote was as follows. You ready? He wrote about a paper. The title of the paper is a very important title: Predictability. Okay, this is what meteorologists want to do. They want to predict the weather. So the title of the paper was Predictability. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? Question mark. That was the title of the paper. And in that paper, what he does was he explains this thing, and he shows this is why it's very hard to predict the weather. It's very hard to predict the weather because you can't keep track of, look what you have to do. You have to keep track of so much information. And his metaphor, his cute little thing is, look, a butterfly in Brazil might flap its wings, and that will cause this, which will cause this, which will cause this, which will cause that, which will cause that, and that might cause tornadoes in Texas. Now, butterflies don't cause tornadoes, whatever, otherwise all the Texans would go down to Brazil and kill out all the butterflies. Okay, in fact, it could be the other way also. Think about this. Let's say there was a tornado coming to Texas, but because a butterfly flapped its wings in Brazil, the tornado was pushed away. So, good things could happen there too. So you have to keep that in mind too. But the point is, his point was, you can't predict things like this. And in fact, the weather is very hard to predict. You could try, they're pretty good for tomorrow, but 2 days or 3 days, it might be an idea to, whatever. I did this as a teenager. I used to cut out the weather we used to get the Post at times and the Daily News in the house, and I used to cut out the weather patterns, the predictions of the weather patterns, and I would keep them. And then I would, the days would go by, and I would look back and see whose weather predictions were better and how long they were. Okay? That's what a nerdy kid does. Anyways, but the point is, yes, we can predict the weather pretty well for the next day or for 2 days, but already for 3 days we're into guessing territory. A week away we're pretty bad at it. Okay? So the idea is as follows. What he came up with, this Lorenz, is he said there are kind of like two types of systems. Okay? One system is a stable system. Stable systems, and I'll see a lot of examples in a second, are things where you can predict the future. You can predict things. For example, I take this. I throw it up. I can predict where it's going to go. In fact, I can even do it with my eyes closed. I won't because it's embarrassing, but I can pretty much predict that this is going to go around 1 or 2 times, etc., etc. Nothing crazy stable. So that's called a stable system. As opposed to that, you have chaotic systems. Weather is a chaotic system because little changes in the weather patterns can make major changes in things. Okay? So because we can't keep track of all the little changes that are going on, therefore we can't make predictions about them. Okay? Let me give you some other examples of chaotic systems. Well, let me give you an example of a stable system. Okay, this is a little bit made up. If you take a Physics 1 class, they spend a lot of time talking about pendulums. Okay, and pendulums go back and forth and back and forth and back and forth and back and forth, and they spend a lot of time talking about how does it depend on the length of the pendulum, does it depend on how long, when does it stop. First-year physics students spend a lot of time doing this. Okay? There's a cute little story about who was the first to formulate these rules about it. Okay? And the story goes about Galileo. we've heard his name before in this class, but Galileo in the 1500s, he grew up in Pisa, and he was going to church, and last summer I was in Pisa and actually went to the house that he was born in and the church that he was in, etc., etc., so I was able to see the candelabras. So basically what happened was, he was this little kid, or 18-year-old, who was in church, and he wasn't interested in listening to what the sermon was. Now, in the church in the 1500s, they didn't have light bulbs, so they used to light the candelabras with candles. And men used to go and they would have a long stick and they would light it. Anyways, the candelabras would act like a pendulum, okay? And he was sitting there and looking at it, and he was checking, figuring out different rules about it. How long does it take till the pendulum stops? How fast does it go? Does it depend on the length? Does it depend on the heaviness of how, this is a heavy candelabra, this is a light candelabra, etc., etc. So does it depend on that? Okay, and he was coming up with different rules. He was, instead of listening to the lecture, you students might know this, he was keeping his eye on the candelabrum, but he needed a measuring device, because he needed a time device. Now this is the 1600s. How do you measure how long it takes? So what he would do is he would put his hand on his heart, okay, thinking that his heart was going at a steady rate, and he would say, oh, look, the pendulum takes 10 times, to do the pendulum to do 10 times takes, 15 heartbeats, okay? He was a little bit off. Why? It's very interesting. Why was he a little bit off? Because his heartbeat started beating faster when it was getting closer to what he wanted it to be. So he was a little bit off. But anyways, he was one of the first people to come up with different rules about these things. And he was a young kid when he was doing this. So this is an example of a stable system. If I throw a ball someplace, it's a stable system, okay, in the following sense. If I throw the ball hard, it's going to go far. If I throw the ball a little less hard, it's going to go a little less far. If I throw the ball a little more hard, it's going to go a little further, okay? Slight changes don't make a difference. Same thing with this. If I do this like this, it's going to go for 15 minutes, and the speed you can calculate, etc., etc. If I do it instead of like this, but like this, a little change, it's going to give you a little change in the output of what's going to be. And that's different than what we saw here. Little changes make major changes. Okay? Let me give you some other examples of chaotic systems. Other examples of chaotic systems. Stock market. There's too many things going on in the stock market that people can't make predictions. If they can make predictions, they would, and they would be very rich. Okay, but there's too many different variables going in there, and a little change, Bill Gates or the head of Amazon just makes a stupid decision over here, thousands of dollars, millions of trades go this way or that way or that way. Lots of strange things could happen. So economics, the stock market is a chaotic system. Biologists, they study how populations go up and down. And algae goes up, and therefore this fish goes down, and this fish goes down, means that fish goes up, etc., etc. These different things can affect each other. Different groups of animals can affect each other. Epidemiologists, okay, we're going through the coronavirus, so epidemiologists do this. And there's a very interesting movie, The Rise of the Planet of the Apes, where this ape has some virus or something like that. He happens to live next door, in this movie, in the modern version of it, he happens to live next door to this guy who is a pilot in an international, he's an international pilot. So because that chimp lived next door to that pilot and he bit him, okay, had he bit somebody who worked in an office, then maybe the people in the office would have gotten sick. But because he worked as an international pilot, he went through every different country and he gave the disease to every different people, and that's why all the humans died out. Okay, so that's a very interesting thing. But again, small change. That's a fiction movie, but not far from it. Okay, patient 0 is always an interesting question. Okay, but little changes in habitat and things like that make major differences in epidemiology. Anyways, physicists study these different types of things also. Okay, a single pendulum, I'd like to show you an example of, I showed you an example of a stable system. This is a stable system. Okay, I'd like to show you a more complicated system, which is a chaotic system. Okay, and this is called a double pendulum. Oops. Okay, it's a, whoops, can you see that? Sorry. It's a pendulum stuck on a pendulum. Okay, now I want to just show you. No, this is not going to work. Sorry. Hold on. Don't move, don't move. Okay, never mind. I'm going to put on the bottom of this YouTube video, I'm going to put a few YouTube videos of double pendulums and triple pendulums. The point of double pendulums and triple pendulums is that it's chaotic. You cannot, you cannot tell what's it going to be, because this thing is affecting this thing, which is affecting this thing, and it gets all cuckoo haywire. And what happens is, if you make a little change over here, you can't really tell the difference between it. You can't, if you make a little change, and I'll show you YouTube videos that do this, you can't really determine what's going to happen and what's not going to happen. Okay? So those beautiful rules that you have for pendulum swinging, they fail when you talk about double pendulums. Okay? And you'll see they get wild. The patterns that they make are just wild and crazy, and not very good. Okay. Okay, so I'll put down some of those different videos, and you can watch them. Great, so those are called chaotic systems. I'd like to explain to you more about chaotic systems and why they're so chaotic. But before we do that, there's another thing I want to show you. It's called a Mandelbrot Set. Okay, a Mandelbrot set. Mandelbrot set is a mathematical construction. I'll put on the bottom. I'll put some links to different Mandelbrot sets. Okay, it's a mathematical construction. It looks something like this. It looks like a little cockroach, in fact. Okay. And the idea is as follows. This structure has a definition, how it's defined, and it's a mathematical definition. But the mathematics depends on small numbers make major changes. Okay? So what you're going to see is, you know, over here it looks like this, but over here it looks totally different, whatever. But the thing is, since it's mathematics, it's not a physical thing. You can probe deeper, you can look deeper and deeper and deeper into it. Okay, and you can see how the mathematics changes. Okay, and it's unbelievable. Now you might say, okay, but eventually it gets smooth. No, this never gets smooth. This never gets smooth. And what they do on the YouTube videos, and I'll put different links to it, is they show you how complicated these things go as you get deeper and deeper into it. And it's very interesting. But the point is, we have mathematics that can somehow mimic chaotic systems. Chaotic systems are different as they go on. Now, I have to tell you a phrase about chaotic systems that is used. It's extremely sensitive to initial conditions. Okay? In other words, it's sensitive to how you start off the problem. Okay? It's sensitive to how you begin talking about these things. Okay, so that's another way of saying a chaotic system is it's extremely sensitive to initial systems, initial states. Great. I want to talk about something else. Again, explaining why these chaotic systems happen. Okay, and again, I'll give you YouTube videos for this. You'll watch it, and it'll be very interesting. Okay, in first semester physics, they do this in high school physics. They have the following formula: F is equal to m1 m2 divided by r squared. You could have a g there. You know, I don't want a g there. Okay, that's complicated enough. Okay, and the idea is as follows: if you have one piece of mass and you have another piece of mass, and then you look at the distance in between these things, you actually look at the distance of their from their center of the mass, but that's not important, then you can tell what the force is going to be between these things. Okay, this is not from Newton, but this is from, I'm sorry, this is not from Galileo, but this is from Newton, who was born the year that Galileo died. Okay, and he came up with this nice formula. And the amazing thing is, and this is a little bit of the history of physics, is that this one formula describes an apple falling from the floor, but it also describes the way the moon goes around the Earth goes around the sun, the way all the planets go, the way all the solar systems go. This is Newton's major thing, that this single little formula describes so much on the planet Earth, terrestrial physics, and outside physics. So that's an amazing thing. And this formula works perfectly for stable systems. Let me just show you. If I made M1 a little bit bigger, if this got a little bit bigger, then this force would get a little bit bigger. If I made M2 a little bit bigger, then this force would get bigger. If I made R2, R squared, a little bit longer, that means separate them, then there's less of an attraction. Okay? If I made R a little bit, if I made R a little bit bigger, if R was bigger, if the distance was bigger, then the force would be, then the force would be smaller because it's the denominator. If R was smaller, in other words, it was closer together, like, and this is why, you know, people feel people don't feel gravity when they're up in space, because there the R is very big, and so the force pulling them down to the planet Earth is very small. If you walk on the moon, you feel much lighter. Why? Because you're not really, you're getting different. There's a difference actually on the planet Earth. If you go take a scale up to Mount Everest and weigh yourself, you weigh a lot thinner. One, because you climbed Mount Everest, that's a lot of exercise, and two, because the pull of gravity is a lot smaller. Great. So this is a typical thing for two-body systems. That's called a two-body system. And again, this could be an apple and the planet Earth. This could be Earth and the moon. This could be two objects just sitting there like this. There is a small attraction to it. Okay, great. But now we can ask, so this is the two-body problem. Okay, and most of college physics, whatever, first semester physics, falls out of this equation. A lot of it falls out from this equation that Galileo did, that Newton did. And again, all those laws about a single pendulum, all the laws about a single pendulum can fall out of this and two or three other small little things. Great. Now let me ask you a question. What's the rule for three bodies? Let's say I have three different bodies, okay? And now I'm going to have distances between these three bodies. So we might call this R12. We'll call this R23. What's the distance between these things? And we'll call this R13. Okay? And now we'd like some formula that describes how these things are going to move, or what's the forces in between moving them. Okay? It would be a nice formula to describe how these things are pushing each other and pulling each other. You ready? You want to see the formula? I don't know of any formula. Nobody knows of any formula. This is called the three-body problem. Two-body problem, totally solvable, easy to figure out. Three-body problem, no one knows the solution. Okay? There is no formula for it. Okay? There's no simple formula for it. Okay? You can... I won't describe what I mean by simple formula, but there is no formula that you can plug into a computer or a calculator and figure out the answer. Okay? So this problem is unsolvable. This is a class on the limits of reason, and we can't solve this basic problem about three bodies. Okay? So that's a little bit of a shocking thing. Okay? But the answer is there's no solution. Let me give you a simple example of a three-body problem. You see? Let me first give you a simple example of a one-body problem, of a two-body problem. Ready? Here's this pendulum, and what's pulling on it? The Earth. Okay? It can't go far because it's stuck to the string, but the Earth is pulling on it, and that's a two-body problem. And you can solve all the equations about a two-body problem. You ready? Great. Now let's go to a three-body problem. This is a three-body problem. Okay? Why? Because there are three bodies, 1, 2, and the planet Earth. Okay? And there are no equations in the world that can figure out how this is going to act and how it's going to act in 10 minutes, etc., etc. I strongly recommend you go look at those videos now, those YouTube videos about the double pendulum, so you can get a feel of what there is. But there's no way in the world you can actually predict what a double pendulum will do. And again, small changes, double pendulums are extremely sensitive to initial conditions. Small changes really make things totally radical. I'd like to give you another example of a three-body problem. Okay? And I always found this to be very, very interesting. Now, if you go to Wikipedia and you ask, how long does it take for the Earth to go around the Sun? In other words, how long is a year? You will get an exact answer. It'll say something like that, 365.24 something something something. I'll give you an exact solution. Okay? We can do it now, but I don't want to do it. Okay? You can see where the 24 comes. Where does the 24 come? I'll tell you where. Let's just give you a little sidebar. If it was 364.25, okay, then this would be 365 and a quarter. So every 4 years should be a leap year. Okay? And every 4 years is a leap year, except it's not 365.24, it's 2.25, it's 0.24. So there's 1/100th, it's 100th off. So we fix the problem. You know how we fix the problem? Every 100 years, every 4 years, every year that's divisible by 4 is a leap year. We make it, instead of 365 days, we make it 366 days. Every 4 years, we do that. Okay? Except if the year is divisible by 100. Okay? Why? Because we need to worry about that extra 100. In the year 1900, 1900 is divisible by 4. It should have been a leap year, but we made it not a leap year. Okay? I'm not sure about the next number, but I think it's a 1. I think maybe it's a 1-5. Great. So we have this rule now. Every 4 years is a leap year, except once every 100 years, to take care of this 100th place. But 1 second. The answer is that would be perfect if the system was this. But how long does it take for the Earth to go around the Sun? It takes this. That's an extra thousandth of a thing. So in order to do that, we have the following exception to our exception. Let's state the entire thing now. Every 4 years is a leap year, except every 100 years, except every 1,000 years. Okay? So in the year 2000, although that's divisible by 100, 2000 is divisible by 100. So let's go through it. Every 4 years every year that's divisible by 4 is a leap year, except years that are divisible by 100. Those are not leap years, except years that are divisible by 1,000. Those are leap years. So the year 2000 was a leap year, okay? Because of this exact notion. We have an exact number that tells you how long does it take, here's the sun, how long does it take for the earth to go around the sun? Sounds good? Great. Okay, great. Now ask yourself the following question. How long does it take for the moon to go around the earth? Okay, so here's the earth, and here's the moon going around the earth. How long does it take for the moon to go around the earth? Now, if you look it up on Wikipedia or you look it up on Google, you can stop right now and say, how long does it take for the moon to go around the earth? Or what is a lunar month? Okay? And if you look it up, it says the following. About 29.5 days. That's what it'll say. Approximately. Say approximately 29.5 days. Now, you could say to yourself, what's that mean? 29.5. They can't find out an exact date. It's 2020. They can't find out how long it takes. They can't measure it exactly. Here, they measure to the 4th digit, to the 10th digit. And they can't give you an exact number. And the answer is, there is no exact number. Okay? This goes up to 6 hours this way or that way. It can go 6 hours longer or 6 hours shorter. It's a lot. It's not a thing. So where do they get this about or approximately? And the answer is they have been doing this for a long time, measuring how long it is till a new moon. Okay? And that measurement, if you take how many days passed for, let's say, 3,000 years, Hindu priests have been doing this for about 3,000 years, divided by how many months you have, you get about 29.5 days. Okay? It's almost, it's an average. It's not an exact thing. So the question is as follows. Why can't they figure out exactly how long it takes the moon? And the answer is because that's a three-body problem. Because let's look at the moon. What is pulling on the moon? Two things are pulling on the moon. The sun is pulling on the moon, and the earth is pulling on the moon. That's a three-body problem. It's a chaotic system. The sun, the earth, and the moon is a chaotic system. They can't figure out how long it's going to take for the moon to go. It is a chaotic system. Okay. Now you might ask yourself, hey, that's stupid. What about the earth? There's two things pulling on the earth also, the sun and the moon. There's two things pulling on the earth, the sun and the moon. So why is it that the earth going around the sun, we have an exact date, an exact thing, but the moon going around the earth, that we take into account? And the answer is as follows. Yes, there are two things pulling on the earth, the sun and the moon. But the sun is so much massively larger than the moon that we can effectively ignore it. We can ignore it. Okay? And so we ignore the moon and we just get this exact date. This is so small compared to the sun, you might as well ignore it. Let me give you another thing. Okay? Here's a three-body problem. Ready? This pen, my body, the earth. Okay? Now, there is a certain pull that this pen has towards my body. I have a pull towards this pen too, but it's not true. Okay? Now watch what happens when I let go of the pen. It ignores the attraction to me. Why? Because the earth is much bigger than I am. Even if I eat 2 pizzas a day, still the earth is much bigger. So basically, we can do exact experiments of how long it takes for this pen to fall to the earth. We ignore the person standing by, because comparatively it's much larger, that thing. Okay? So, but here's a real live example where you can see the difference between 2 and 3, the two-body problem and the three-body problem. Okay? Now, that's the two-body problem and three-body problem. What about the four-body problem? What about the four-body problem? Anyways, that's totally not knowable at all. Okay? And you can go, we have something called the n-body problem. Okay? And again, we can't do it. So, physicists are great at predicting two-body problems, stable systems. But when they get harder, things get more complicated and they can't figure it out. It's beyond the limits of reason. Okay, I just want to go through a few little things. Chaotic systems, the butterfly effect, that's where we get this phrase, the butterfly effect, from this paper by Lorenz. Butterfly flaps its wings in Brazil. Can it cause a thing in Texas? A tornado in Texas. Okay? Now, the main thing is as follows. These things are deterministic. The universe follows rules. Okay? Yes, I cannot predict how this is going to swing, but it's not random. The universe has some rules. We can't write down the rules, but it follows exact rules of how things are going. So that's called deterministic. As opposed to that, random is when there are no rules, and they're not like that at all. And physicists tell us that quantum mechanics, well, some physicists tell us that quantum mechanics, and something we talked about a little bit when we talked about quantum computing, is random. It's beyond, it's not only that human beings can't determine what it is, but it's beyond that. Okay, there is a nice there's a nice picture on page 174. Don't move. Okay, by the way, here's a nice picture of the Mandelbrot set, and again, you'll see that in the book, and you'll see that in the thing. Here's that picture of a two-body problem and a three-body problem, and we talk about that. And then here's a nice picture of all the different types of systems that you can have. Stable systems, what long-term predictable, how you can predict things long-term, how you can only predict things short-term. For example, the weather, you can predict a little bit tomorrow or the next day. All these things are what's called deterministic, means you can follow. And here's examples of things that are deterministic. And out here, things that are not deterministic are random. And as far as we know, the only thing we have that's random is quantum mechanics. But everything runs by quantum mechanics, so maybe there is a certain amount of randomness. I'm begging you, I really think it would be a good idea if you read through this section. It's a very easy section to read, and it's got a lot of interesting things. Okay, now we're going to take a 1-minute break, and then we're going to come back and we're going to do section 9.1. Hi. So now we're doing chapter 9, and chapter 9 is a little bit about mathematics, and it's just about numbers in mathematics. So, again, I want to start off with a little story. There was a man named Pythagoras. And Pythagoras, we know him from Pythagoras Theorem, okay, which says that a squared plus b squared is equal to c squared. Okay, so we like that theorem because we learn it very young, and it's important. Okay. Great. Okay, so Pythagoras was a real guy who lived about 500 BC, 600 BC, and he started a religion, which is a very good thing because you get people to like you and you make a lot of money, and it's a good idea. Okay, in his religion, it said as follows. He said, numbers control everything. Now, when you take a physics course, you realize that's in fact true. In order to describe how the world works, you have to know a lot of mathematics beforehand. Okay, and the reason for that is because numbers control everything. But he said there were specific types of numbers that control things. Okay, we know these numbers already because we dealt with them in chapter 4. The natural numbers and ratios of the natural numbers, which we call fractions, rational numbers. Okay, so what Mr. Pythagoras said is, you know what? Only these types of things exist. Everything else doesn't really exist. And you have to understand, this is ancient Greece. They didn't have negative numbers. They didn't have other things like that. But they didn't talk about real numbers either. They didn't think that there was any type of number that wasn't, they didn't think of any type of number that wasn't in here, Q. Okay? Now, he had a student, his student's name was, got to write it down because I'm not going to remember it, Hippasus. Okay? And Hippasus had the following thing. Okay? He said, take a square. Take any square whatsoever. Okay, we'll say this is a 1 foot by 1 foot. Now look at the diagonal. Okay? The diagonal, let's use Pythagorean. He was a student of his, so he knew Pythagorean theorem. He said this is 1 squared plus 1 squared. This is going to be the square root of 1 squared plus 1 squared is square root of 2. Okay, let's just make sure that works. 1 squared plus 1 squared is equal to square root of 2 squared is 2. So 1 plus 1 is equal to 2. Okay, so that works. Okay, but then he showed an amazing thing. The square root of 2 is not equal to a over b. Okay? He showed that the square root of 2 is not equal to a fraction. It is not a fraction. It is an irrational number. So fractions are called rational numbers. They're rational, not that they're intelligent, but they're rational numbers. When you have a number that's not a fraction, it's called an irrational number. Okay, it's not rational. Now, his teacher, Mr. Pythagoras, said no such things exist. But he just proved that, yes, they do. They do exist. Okay, great. I'd like to spend 1 minute showing you that proof. Now, it's not his proof. Hold on. It's not his proof, but it is a proof, and I'd like to show it to you. It's a very pretty proof. It's very, what's called geometric. And it goes as follows. It's a proof by contradiction. We're used to that. We know what a proof by contradiction is because we've dealt with them before. It says as follows. Let's say square root, well, let's do a theorem. Theorem, square root of 2 is not equal to a over b. They are not equal to. Now we're going to prove it by contradiction. We're going to assume square root of 2 is equal to a over b, and we're going to get a contradiction. Okay, so let's do it. So let's assume this is equal. We're going to square both sides. Square both sides, we get 2 is equal to a squared over b squared. I just squared both sides. If this is equal to this, then you can square both sides, you get that. Okay, another way of saying that is 2 times b squared is equal to a squared. Okay, now this proof is fairly new. It was told to me about, it's not ancient Greek, but it's nice. Okay, great. So what this means is there's some b and there's some a, and 2b squared is equal to a squared. Now, there are a lot of different fractions that may do this. I'm going to choose a and b the smallest. In other words, I can't get smaller than that. That's one of the assumptions we have to make. In other words, it's equal to a fraction, but rather than saying, you know, the fraction 2 over 3 is equal to 200 over 300. Okay? But I want to assume I'm getting it in the smallest possible thing. So we're not talking about this, we're talking about that. Great. Okay. So let me just go through what exactly this means, that 2 squares are equal to 1 square. So what that means is as follows. There's a square. Each side is equal to a. Oops. Okay. Okay. And there are two squares that fit into it, that are the same size as it. So we might write those two squares like this. They're going to be a little bit smaller than A. They're going to be size B. Okay. And the idea is, if these two squares is equal to this square, then these two squares fit in like this. Okay? I'm going to color these squares. You'll see why in a second. Okay, great. Okay, and now I'm going to put these two squares inside. Now they're not going to fit perfectly well. They are not going to fit perfectly well. Okay, but that's the way squares work. They don't, you know, if this was a longer thing, then maybe we could fit them in, but they don't. Okay, so this one is going to go here, and this one is going to go here. Great. Now, let's analyze this a little bit. Okay? What I said was A squared should be the same size as B, 2B squared. Okay, two of those. Now, I put them in like this, but notice there's two problems here. One, I missed some space. Okay? Two, I overlapped some space. Okay, there's overlap. This is overlap. Now, if this was in fact true, then what can we say? Look, the shapes don't fit in nicely, but the overlap is the same size as the two empties, right? If you're going to say that, look, you counted this twice, well, that means that this overlap, okay, 1 and 1 would be the same as that, which means that this square, let's call it size C, okay, is the same thing as these two smaller squares. Let's call them D, size D. Okay, again, because there's an overlap, that means I counted this area twice. But I missed out these two areas. Okay? Now, the very fact that they have to be equal means that, ready, 2 times D squared, this size is D squared, this size is D squared, is equal to C squared. Okay? Another way of saying that is 2 is equal to C squared over D squared. Another way of saying that is square root of 2 is equal to C over D. Now, C and D are smaller than A and B, but we assumed these were the smallest possible ones. What are you telling me? You found me another smaller one that's even smaller than this, but you assumed this was smallest. How could it be? Must be a contradiction. Okay, must be a contradiction. Okay, so that's a nice little proof. So again, we assume there is such a thing, and we found a small, we assume there is such a thing of smallest type, and you know what? We find another one which is even smaller. Doesn't make sense. Conclusion, it never existed in the first place. Okay, so this is a proof that square root of 2 is not equal to A over B. Okay, great. So let's just go over here. Let's erase this. Okay, this is done in the book, and it's a very pretty proof. It's really pretty. Okay, it's really nice. Okay, so what I'm going to talk about now is, and we did this a little bit in the beginning of chapter 4 with different number systems, but we're going to start off talking about little number systems that we know already. So we have the natural numbers, and we have the fractions. Okay? And we know that natural numbers sit inside the fractions. The number 5 is really 5 over 1. Not so hard. Okay, so we have that. And what I just showed you, or what Mr. Hippasus, I forgot to tell you what happened with the Mr. Hippasus. So Pythagoras started this religion that says that only the natural numbers and the real and the fractions exist and they control the world. And here comes his student Hippasus, okay, who talks about the square root of 2, and he proved that the square root of 2 is not inside there, it's not a fraction. Okay, guess what they did to Mr. Hippasus? They took him out to sea and they threw him into the sea to make sure that he doesn't tell anybody about this violation of Pythagoras Theorem. That's the way the legend works. Okay? Great. Okay? Now, so in some sense this is, if you want, it's a limitation of the science of 2,500 years ago. In other words, in the science of 2,500 years ago, they thought that only this exists, but really there's a lot more. And we're going to talk more about other things. Let me just show you some other things that ancient Greeks talked about as impossibilities, mathematical things. Okay? And they are as follows. Okay, we're going to get back to this. Don't destroy this. We need this in your notes. You've seen this. This is called a compass. Okay? It has a sharp point over here, and it has a pencil over here, okay, and an eraser over here, okay, and the pencil's over here, and that's called a compass, okay, and then there's something called a straight edge, like this. Now the physicists were the philosophers, or the Greek philosophers, were very excited about these things, and they spent a lot of time showing what you can construct with this and what you can't. In 10th grade math, when I went to 10th grade math, they had a lot of things like this. Okay, they taught you how to bisect an angle using this. They taught you how to double a line. Here's one line, make it the same size as that. They taught you how to make a square with this angle or stuff like that. They dealt with a lot of things, and these are things that you can do just with these things and these things. Okay. Okay, so let's think about these in terms of numbers. Oh, one second. Before we do that, I'd like to show you 3 constructions that they can't do with this. So again, our class is about things that science can't do. So we're going to talk about, here's the science of ancient Greece. Let me show you 3 things that ancient Greece was not able to do with these straight edge and things. So one thing is called squaring the circle. Okay, let me tell you what it's about. Let's say I give you a circle. It has a certain area. Okay, it has a certain area. I don't want to get into the math of it, but I would like to make a circle that has the same area as, make a square that has the same area as the circle. Okay? It turns out you cannot do that. And again, the ancient Greeks spent hundreds of years trying to do it, trying to find proofs for it, but they couldn't do it. You cannot make a circle that has the same area. You cannot make a square that has the same area as a given circle. In other words, you can try, you can put the compass here, you can put the other edge here. They can't do it. So that's one thing. Another thing that was very hard for them to, not very hard, they couldn't do it, is called trisecting the angle. I just said you can bisect an angle, you can split an angle in half. In other words, if I give you an angle, I can find an area such that this angle is equal to that angle. That's easy to bisect, bi as in 2, bisect an angle. Okay? But the ancient Greeks, they asked the following thing. I want to trisect an angle. In other words, I want this to be the same as this is this. So alpha, alpha, alpha. All 3 of them should be the same thing. That's called trisecting an angle. Okay? They tried as hard as they could, they tried with many ways, and nowadays we can prove that it can't be done. with a straight edge and a ruler. Now I can easily do it very simply. If I give me an angle, measure how big the angle is, open up my calculator, divide it by 3, divided by 3, divided by 3. You can do that without a calculator, dividing by 3, and then make that angle the way it is. But that's not using a straight edge and a compass. That's using modern day measuring how big the thing is. And the Greeks didn't like that. They felt that mathematics should be constructable. And by constructable, they meant with a straight edge and a compass. Okay? Let me just tell you a third thing that they tried and failed because it cannot be done, and that's called doubling the square. Okay? Doubling the square. Doubling the square. Let me just show you what that's about. Okay, so I'm sorry, I didn't do the right thing. The idea here is, given an angle, trisect the angle. 1, 2. Okay, such that these three things are the same. Now, let me tell you what doubling the square is. Let's say I give you on a piece of paper a picture of a square. Okay. Not the greatest artist, but we can do this. That's a nice square. Now, a square has a certain volume. I'll just make sure that you can see this. Yeah, you can see that. A square has a certain volume. In other words, these are all the same. This is A. The height, the width, the length is all A, so this is A to the third. A to the third. Okay? Great. What I'd like to do is, using a straight edge and a compass, double the square. Double the volume. So make another square. Okay, make another square whose sizes should be B. Okay, so the volume will be B to the third, and what I want is B to the third should equal to 2 times A to the third. Okay, in other words, find me a B that does this. You can take the cube root of both sides, you get B is equal to the cube root of 2 times A. So if you could just find me the cube root of 2, then you can get it. Okay? These are 3 problems that ancient Greeks tried to solve, but they couldn't solve. Okay? These are 3 problems that the ancient Greeks had to try to solve using a straight edge and a compass, and they couldn't solve. And then nowadays we figured out why they couldn't do it and realized it cannot be done. Okay? It cannot be done. Great. So, but these numbers, okay, hold on. You can do a lot with the straight edge and the compass. In particular, if I give you one number, you can add it together to itself. You can double the number. You can double the number again. Okay? You can also, if I give you 2 sizes, using a straight edge and a number, you can add them together. So you can, if this is X and this is Y, you can put them together and get X plus Y. That's X plus Y. So you can do a lot of things. Also, if I give you X and Y, you can get a length who's going to be X divided by Y. Okay? Conclusion, you can get all the natural numbers and you can get fractions of the numbers. But more importantly, there's a lot of other things you can get, and these are called constructable numbers. Constructable numbers. Numbers that you can construct using the straight edge and the thing. And it turns out the natural numbers sit in the rational numbers, that we know, but the rational numbers, because you can get 2 rational numbers, you can divide them, they sit in the constructible numbers. Great. Now, there are other things also. Hold epsilon, but besides that, what I just showed was that you cannot, out here, the cube root of 2 is out there. It's not constructible. There's no way in the world you can construct it. The cube root of 2 is not a constructible number. It's out there. Okay? And because it's not a constructible number, we have to talk about something larger than this. And the thing that we call is algebraic. Okay? Let me show you what an algebraic number is. Okay? Definition. An algebraic number is a solution to a polynomial with integers, coefficients. Okay? An algebraic number, so that's what we're describing, is a solution to a polynomial with integer coefficients. Let me just show you what it means. It's not a hard thing at all. Consider the following. X minus 5 equals 0. Solve for x. Answer, 5. Okay. X minus 20 equals 0. 20 is the solution to this. Okay. So what I just showed you is algebraic numbers contain natural numbers too. Okay. Natural numbers are examples of these. Okay. Great. How about the following? 5x minus 7 equals 0. What's the solution to this? Okay, and the answer is bring the 7 over. I get 5x equals 7. Divide by 5, I get x equals 7 over 5. Okay, so fractions are algebraic numbers. Okay. Give me any fraction, a over b. Well, here's a polynomial that does this. Ax minus b equals 0. Solve for x. Bring the b over. Divide by a. Oh, I'm sorry, I did this wrong. Okay. Okay. Bring the a over. Divide by b. I get x is equal to a over b. So fractions are algebraic numbers, okay? But more importantly, ready? How about that? X squared minus 2, that's an integer. This has a 1 in front of it, that's an integer. How about that? Well, let's solve for x. X equals, bring the 2 over. X squared is equal to 2. Take the square root of both sides. I get x is equal to square root of 2. So square root of 2 is not a fraction. We showed that 2 minutes ago, but it is algebraic. Fine. Let me show you. How about that? Well, how about that? That's x to the third minus 2 is equal to 0. Let's bring the 2 over. I get x to the third is equal to 2. Take the cube root of both sides. X is equal to the cube root of 2. So even numbers that are not constructible are still algebraic. Okay? Okay. Now, 5x to the 6 minus 28x to the 5th plus 14x to the 3rd minus 17x plus 29 equals 0. What's the solution to this? I have no idea what the solution to is. But, okay, whatever the solution to this is, okay, it's an algebraic number. It goes in there. Okay, great. Great. Question, are there numbers that are not algebraic? Well, let's see. What numbers do we have? We have the real numbers. Remember the real numbers? That's what you got drawn the first day. That's the real numbers. Okay? This has every possible number whatsoever. Okay? Question. What's out here? Okay? And the answer is, so I can't get bigger than the real numbers. I don't want to talk about complex numbers and things like that. I can't get bigger than the real numbers. But what's out here? And the answer is, these are called transcendental numbers. These are real numbers that are not algebraic. Let me give you some examples of transcendental numbers. Transcendental numbers are real numbers that are not algebraic. Okay? Let me give you an example of such a thing. Pi. Pi can't be written as a polynomial. E can't be written as a polynomial. Okay? And lots of other, if you don't know what E is, that's fine. But E is a famous number that goes in there. Great. Now, great. So transcendental numbers are out here. Okay. Okay, so you have pi is over here. There's no fraction for pi. You have E is over here. Okay, that's the end of our hierarchy of numbers. But I want to do the following. I want to think about ways of describing numbers. Again, this is the math part, so the basic type of math that we do is describing numbers. Well, how do you describe a natural number? You just give the person a number. How do you describe a rational number? You give two numbers. How do you decide a constructible number? Well, you have to give like a little algorithm of how you construct this number. But it's not hard, it's a bunch of steps. Fine, it's doable. How do you give an algebraic number? How do you describe an algebraic number? How do you say a number is algebraic? Well, you give the polynomial. You say, okay, here's a polynomial, and that polynomial, the solution to that polynomial is this algebraic number. Very simple. Okay? Great. How about out here? Okay? So, you can't describe them. I mean, I can describe pi. I can say pi is the ratio of the circumference to the diameter or something. E is something that you learn in Calc 1, etc., etc. But I can't write out a nice formula to give you this thing. It's beyond description. Okay, great. Now you might say to me, hey, big deal, you found two of them. In fact, it wasn't until the 1880s that they actually proved that these numbers were transcendental. They don't have a lot of proofs that it's very hard to prove that a number is not algebraic. Well, I can't make a formula for it? Well, maybe. And so it's very hard to do. But I'd like to do an interesting counting argument. Question. How many elements are in the real numbers? Okay? And the answer is, we know this from chapter 4, uncountably infinite. Good. Okay. How many numbers are algebraic? Whoops. How many numbers are algebraic? Okay. And the answer is countably infinite. Okay. Because you can describe polynomials, you can give the numbers of their coefficients, you can describe them very simple. They're not, you don't have a lot of them. Anyways, yes, there are infinite number of them, but they're countably infinite. And we know the difference between uncountably infinite and countably infinite. There's a vastly, vastly, vastly more of these guys than there are these guys. Vastly more of these guys than these guys. This is not drawn to scale. If we were to draw it to scale, it would look something like this. Here's the real numbers, and here's the algebraic numbers. Even that is not really to scale. And inside that is the constructible, and inside that is the Most numbers are transcendental, although we can't, it's hard to prove which numbers are, but most numbers are transcendental. However, the vast majority of numbers are transcendental, but we only deal with these algebraic numbers. These are the only numbers we really are easy to describe. Okay, so you have to keep this hierarchy in mind. Great. So this is just a taste of some of the math things that are, again, beyond reason, beyond our ability to do. and it's a very interesting chapter. You're welcome to read it. Okay, we have homework questions for section 7.1 and 9.1, which I'll do in person, but I really think you should try to do it, and look at the videos at the bottom of the thing, and everything is totally understandable. Have a wonderful day. It's been a great time. My goal in this class was to show you that there are a lot of interesting things that are beyond people's ability to know, to understand, to deal with. Anyways, take care. Thank you. I hope you read the book. I hope you enjoy it.